Okay. Okay, so welcome here tonight for tonight's Royal Aero Society lecture, and welcome to everyone that's joining us remotely. So tonight it's my great pleasure to welcome Professor James Scanlan here to give us our lecture. So James Scanlan works at an executive level for Airbus, managing complex international research projects for worth over 20 million in value before joining academia. And his final post at Airbus was the head of manufacturing research, and that was in 1990. Is that correct, Jim? Long time ago now. He currently co-directs the Rolls-Royce University Technology Centre in Design at Southampton, which has attracted an income over £15 million. In 2009, he was awarded the Rolls-Royce Technical Director's Prize for Research Innovation. He has an interest in design research and in particularly how complex systems, in particular aerospace systems, can be optimized. More recently, he has established a large group at Southampton that undertakes research into unmanned aircraft systems. And Jim has been the principal investigator on grants and industry income of over 25 million from the university from this time in academia. I'll hand it over to you, Jim.
Thanks very much. So, good evening, everyone. This talk is primarily about this thing here, an airframe called Ultra, and I'm going to be talking about a number of things, time permitting, and Scott will alert me if I'm overgoing my time. Quick introduction. I then want to talk about what I call the talent pipeline, so the brilliant people that we have working on these systems. It's largely a homegrown pipeline of Southampton graduates. I then want to get into the platform itself and say a little bit about what it does, how it was designed, how we designed it. Then I'm going to zoom in a little bit onto the avionics. So the avionics have been developed at Southampton. Say a bit about operations. So we've been operating these platforms all over the UK. And if we've got time, maybe talk about future airspace. So Scott mentioned we've got quite a large group here under the banner Soften UAV, and we've got a website if people are interested in seeing more about it. Large critical mass doing these kinds of things. So some are the historical platforms, doing all sorts of weird and wonderful things. This platform up here, remind me how I use. Yeah, this platform down here, yeah, is due to fly over a volcano in Guatemala early next year, etc., etc. This isn't a shameless plug, but over the years, we captured a lot of our experience in this book. My colleagues and I put down our practical experience in developing platforms in this book. And we hope that's useful to undergraduates and perhaps others. And I run an EPSRC program grant. We've got 18 months of this grant to go. So it was a 5-year grant with 5 total universities doing various research activities associated with drones. And this was an event we had before COVID, and we were planning to do this every year. At Lambeda, we were flying all sorts of platforms and doing all sorts of research associated with a variety of platforms on the ground. So I think it's quite important to just talk about the talent pipeline, because none of this would be possible without the brilliant people we have access to at Southampton, and say a bit about what we believe is important in helping develop that pipeline. So roughly 10 years ago at Southampton, we decided to make a bit of a change the way that we teach what's known as systems design teaching, so typical of aerospace products. And we started to embrace a thing called CDIO, so conceive, design, integrate, and operate. So basically hands-on and closing the loop. So designing something, but actually then building it and operating it and checking whether your predictions were correct. So we have hands-on activity, and it's quite unusual on aerospace courses to have the level of hands-on activity we have from years 1 to 4. So in every year, the students have to do something hands-on, COVID permitting, of course. And we've invested a lot in design and build studios and student-led workshops. And I want to talk about a couple of examples of the CDO-IO teaching that we do in the various years. So in part 2, we issue students with a fuselage, and the job is to design a wing system that allows this aircraft to travel with the greatest speed range, so fly fast and slowly. But more than that, the student team, so they're typically working in teams of 5, have to design an avionics system. So at the very minimum, it has to be a black box flight recorder, up to a rudimentary autopilot and auto stabilization system. So quite a challenging project for second year students. And they're catapult launched so that every single aircraft gets the same impetus, so it's fair. In the past, we used to have them hand launched, and it depended on how strong the launcher was. So we now use a catapult system for this. So what? Well, we learn a lot from our mistakes. And if I can get this playing. If you could just see why that isn't playing. Lovely, thanks. So this is one of the student teams, and it didn't end very well. And the so what from that is the theoretical stuff we teach on the course about things like VNE, control surface reversal, divergence, flutter. And boy, do people understand that stuff when they see one of their wonderful creations fall out of the sky. And we also do structural testing of every single wing in part 2. So we measure the stiffness to weight ratio, torsional stiffness, the distance of flexor axis from the leading edge. And sure enough, the aeroplane that failed and the wing that failed was the one that didn't perform very well in those tests. So harsh lessons, but the message we give our students is to learn from your mistakes. And then we operate a thing called a group design project in the 4th year, so the capstone group design project. This aeroplane here was our first gas turbine aeroplane. It was very exciting, again, pre-COVID. But we invest a lot of effort and a lot of facilities in making sure these are quite realistic projects. I noticed 1 or 2 people in the room are actually going through this process as we speak, but quite well resourced with some fixed timescales to design something and operate something and prove that it meets design predictions. And then we have an annual, again, COVID permitting. Sadly, we haven't done it for a couple of years, an annual Southampton Air Show where we go to a local facility and we actually put the aircraft through their paces. We instrument the aircraft. We have some very sophisticated camera technology to record every single flight and do proper flight testing. So here is one of our brilliant graduates. So Andrew Locke is the chief designer for the Ultra platform. So Ultra stands for Unmanned Low-Cost Transport Aircraft. And what is the point of this aircraft? So what was it designed to do? The purpose is to ship food aid cheaply, long range, reasonable quantities in places like South Sudan and other challenging areas, because there is a terrible transport infrastructure in places like this, and this is potentially the cheapest way to feed large numbers of people. And this project is the brainchild of Stephen Wright and Charles Scales, shown here. This is somewhat of a celebration a couple of weeks ago because we've just completed some flight testing, some very challenging flight testing. You'll see bottles of champagne in hands. And it's a very ambitious project that we're proving in the UK before probably May next year. We start going out to Africa to fly this for real. So the platform itself, it's something like, it's getting on for a half-ton aeroplane, so it's a very significant aeroplane. It's no longer a small toy. It's a very serious aerospace product. Originally 350 kilos, but it's now actually 450 kilos MTOW. It's capable of carrying 100 kilos payload, so that's a very useful load. If you think of bags of corn, maize, food products, it's a very significant load. It's capable of flying for 1,000 kilometers. You'll see the design of the fuselage. It's essentially a flying wing. It's certainly got a wing-like center section that produces useful lift. But it's the great advantage of that is that it's a very capacious aeroplane, so it can carry 700 litres, 10 metres wingspan. And something I'm going to talk about in this talk, I'm going to talk about autonomy, and I'm going to talk about safety and redundant critical systems, because this thing will have a remote pilot. We need to focus on reliability. We can't afford for these things going out of control and making large holes in the ground. So we try and practice what we preach. So we teach a lot at Southampton about formal design process, systematic design, and that's exactly what we've done in the development of this airplane. So looking at configurations, early configuration studies, we did a lot of detailed calculations, performance predictions of a variety of configurations before we homed in on the configuration we particularly liked. And we captured in this thing, this is our design rationale tree. This is an enormous document that has captured all our decision making and the justification around every single decision, from size of tires to type of undercarriage to what servo to use in the tail, for example, all captured very formally in this document, so we can review it, and if we want to change decisions, we can actually add information. We're lucky at Southampton, we've got a large wind tunnel, so once we'd settled the configuration, we focused on wind tunnel studies, and particularly looking at how to match the best L over D of this lifting body with the best L over D of the main wing section at cruise, for example. An example of the sort of detailed analysis, simple question: should we have strut brace wings like Cessna 172s, for example, or should we have a cantilever wing? And there's pros and cons. And again, we did, led by Andrew, a lot of detailed analysis comparing the two. And we reckon that actually having a strut-based wing overall gives us advantages. Obviously, it's a bit more draggy, but it gives us structural advantages in terms of our large payload bay. And so here's some photos of that payload bay. You can see it carries quite a lot of payload. We set out on this project to design an airplane that's as easy to load as a hatchback car, and this is. So this has gas struts on the rear fairing. You simply open it up and throw things into the cavernous payload bay. The great thing is that the payload bay largely sits on the C of G, so you can't upset the C of G by poor loading of payload. And as I said, 700 litres is a very useful volume. And in fact, the density of stuff that we've been shipping for the Royal Mail, as shown here, is about the 100 kilos for 700 litres. So we've got that density capability. Often aircraft bulk out before they weight out effectively. So payload. And then we applied a thing that I feel very passionate about, a thing called value-driven design. So making sure you've designed the right product, the right price point, you haven't over-engineered your product. And because this was shipping, and it's designed to ship, you know, bags of corn and bags of rice, which are, the World Food Programme buys these for about 5p a bag. So it's not high-value payload. You can't afford a very expensive platform to move this around. So we focused a lot on cost of operations and therefore cost of the platform. So you'll notice that the aircraft is almost entirely single curvature, so it's simple to make. We avoided composites like the plague because aluminium is A, cheap and very repairable. So imagine we have an incident or some damage out in the field. It's very easy to repair aluminium, not so easy to repair composites out in the field. It's a highly modular structure, so you'll notice, you can see the control surfaces on the wing. Every one of those control surfaces, including the vertical, the horizontal control surfaces, the ailerons, the flaps, are identical, interchangeable control surfaces. So we can have spares, and if one of them goes wrong, we can change them over very quickly. Low-cost engines, so we happen to use Briggs & Stratton engines, despite the fact that, you know, they have connotations of lawnmower engines. They're actually very sophisticated engines, so they're fuel injected. They have a very high mean time between overhaul, very respectable in that regard. And our philosophy of what we call over-actuation is a lesson we learned on previous aircraft. So this is our spotter aircraft. So this is a 4-meter wingspan airplane. And you'll notice we actually have split ailerons. So we've got some redundancy. So if a servo fails or some mechanical failure occurs, we've still got control of the aircraft. On our Ultra aircraft, we actually had 24 control surfaces, so lots of redundancy. And that spills over into the propulsion. So we have 2 engines, and it's capable of flying on a single engine. So if we've got an engine failure, we can carry on the mission or return to base. And, you know, the sort of thing we try and convince our students is that using a formal design process actually pays dividends. So we religiously followed a very systematic process. And the payoff is that we don't really have any regrets. We got most of the important design decisions correct. We wouldn't go back and say, oh, I prefer to have a cantilever wing, or I prefer to change the configuration. We got all the big things right. The calculations were verified, so the structural calculations were verified with structural testing. So we were required by the CAA to actually load the structure with limit loads to prove our calculations. Very bad news if you get those wrong, because you've probably damaged a very expensive airframe, and you've got to go back and redesign. We had a very rigorous CAA audit. So CAA, we have to seek permission from them to fly these around the UK and potentially put people at risk, put other airspace users at risk. And we passed a very rigorous CAA audit in October of this year. And the airframe is very robust. So we have been flying, and I'm going to show you some of the flying shortly, in 40-knot wind gusts, very poor weather. The platform is very capable. We've already had an MTOW increase. We're going from 350 kilo MTOW to the latest iteration, which is 450 kilos. And that's as a result of the good design principles we used very early on. So I said I'd talk about the avionics, and again, some brilliant ex-Southampton graduates who have now formed a company called Distributed Avionics, and they do give me freebies every now and again. So I want to talk about this, what, why, and why is it so important on this aeroplane. I don't know how many people on the call and in this room have heard of this thing, but I happen to read accident reports. I read accident reports because you can learn a lot from things that went wrong. And it was about 18 months ago, I can't remember the exact date, this thing, which is nearly 100 kilos, so quite a big, heavy object, was doing a demonstration flight at Goodwood and went out of control. And it went badly out of control because it climbed to 8,000 feet, entered controlled airspace, caused all sorts of alarm at Gatwick before the batteries ran out, and it fell, luckily, into a field and didn't kill anyone or damage any property. But there was lessons learned from this. For those of you interested in these things, the AAIB report is fantastic. It's full of all sorts of gems. But to be blunt, this wasn't an airworthy platform. They shouldn't have been given permission to fly. It was too dangerous. And certainly, we're required to write safety cases to do this stuff. And I don't write safety cases for the CAA. I write them for me, and I want to have a clear conscience and make sure that we're doing things responsibly and not putting people's lives in danger. So we focus a lot on super reliable systems, particularly the autopilots. And so typical autopilots in civil aircraft have to have high levels of trust, of course, and they tend to use multiple redundant hardware and software systems, therefore several flight computers, typically 3, so triple redundant systems with a thing called an arbiter. And the arbiter is the thing that sits over them and checks that they're all functioning correctly and deciding which one should fly the airplane. The problem is that having an arbiter means that you still have a single point of failure in your systems. And actually, because these systems are highly regulated and highly certified, to be honest, the flight control layer is reasonably robust. But the vulnerability has shifted to what I call the sensing layer. And there's many examples of recent air disasters where sensing discrepancies caused the total loss of an aircraft. And some of these are very famous incidents. 2 recent Boeing 737 incidents, for example. So, you know, over 600 recent fatalities because arguably the flight control system had problems. And actually many large military UAV crashes, again, things like pitot-static systems just being faulty, essentially. And there's a recent document called SORA, Specific Operations Risk Assessment, that is going to be adopted as a way to certify these platforms in the future, or give permission for these platforms in the future. And there's a really nice thing in SORA, top line there, robustness is a function of assurance or integrity or a combination of both. And assurance is the certification, the writing of safety critical code to DO 178 standards, for example. And that's typically what the aircraft industry would do, but it's extremely expensive to follow those processes. So, for example, if you take software, writing a line of commercial code, you have to multiply the cost of that by roughly 100 to account for the cost of safety critical code, for example. So assurance is essentially certification. The alternative is integrity, so as a measure of the inherent elegance of the design and architecture. And that's the one we focused on in the work that we did. And actually, the computer science community, this is a very vibrant area of research. So creating mathematical representation of catastrophic failure, where the systems actors must agree on a concerted strategy. And the phrase Byzantine generals problem was coined by a chap called Lamport. Lamport, you may have heard of, he's a very famous computer scientist. He wrote LaTeX, so any PhD students in the room will know that that's the tool to write text documents in. So it's referred to as the Byzantine generals problem. The idea is that you've got a bunch of generals trying to invade a castle. If they coordinate and collaborate, they will be assured of victory. If they don't, they will be defeated. And the subtlety here is that these generals don't just fail, they also tell lies, they're traitorous. And that's the problem that we had in a lot of the aerospace incidents here, in that sadly you had sensors that were giving wrong but plausible outputs. And the problem is, which one do you believe? You're at 30,000 feet, it's dark, suddenly something goes wrong, and you've got two systems, one saying you're flying at 10 degrees angle of attack, and another saying 30 degrees angle of attack. What do you do? And that's a very difficult problem. And actually locked into this is the mathematics, which is dependent on the architecture. One of the things that we've challenged is the architecture of all of this. And so what we have here is a Monte Carlo simulation, very naive and simplistic, I have to add, of a traditional triple redundant autopilot system. And if you run a Monte Carlo and just randomly get things to fail, what I call the functional state space is about 5%, i.e. not very good. In other words, it's quite a vulnerable system architecturally. And what we did, we took the same resources, we weren't cheating and throwing loads of stuff at it, but by changing the architecture and using what we call a distributed masterless architecture, you get an order of magnitude improvement in redundancy and reliability. So going back to brilliant undergraduates, brilliant team, brilliant students, this was an idea I discussed particularly with Joe Roberts, an undergraduate at the time, but now one of our team, and said, do you fancy doing a GDP around this? The team produced this wonderful airplane that proved the principles of distributed systems. You can see an insane number of control surfaces, an insane number of pitot-static systems, just to prove the idea. And this was developed so at the Cascade Lambeda flight test range. This was the first flight of a truly masterless flight control system. What that means is there's no arbiter. You have peer flight processors that are all essentially in control of the aircraft. I mean, one of them fails, it doesn't matter. The thing just seamlessly moves on. So that's what we use to fly our aeroplane. And Distributed Avionics has now got a patent. We mounted a successful IP defense against the likes of Boeing, Airbus, Lockheed Martin, who all thought they'd got this covered. But no, we've been granted a patent actually this year. And that's what it looks like. Some really nice, super reliable, robust, very respectable avionics gear to fly this quite big and potentially dangerous aeroplane. And if you want to find out more about it, you can click on the link there. So, operations, how are we doing for time? Let me whiz through operations. So, 2020 for us was an incredibly busy year. So on the 9th of May, we flew the platform between the or the mainland and Isle of Wight, and it was the first point-to-point BV loss, beyond visual line of sight flight in the UK. And then not long afterwards, we flew a fairly long mission. So to us, 50 kilometres is quite a long mission, flying from the mainland and the Isles of Scilly. And this is the Isle of Wight flight. The scary thing here was that we had to do single engine operation tests to satisfy the CAA. So not just throttling back, actually shutting down port engine, then recovering, shutting down starboard engine, proving the aircraft could fly, at least maintain altitude on a single engine. So this is the aircraft approaching the Isle of Wight. We had base stations either side. We had all sorts of comms stuff set up. And it's actually a very small airstrip. So airstrip called Finstead. Fingers crossed the brakes work okay. We don't fancy going in the hedge at the end of the runway. But it all went well, but it was pretty stressful, to say the least. We then followed it up a more ambitious flight, so flying what's known as the Isles of Scilly Air Bridge. And this was quite different in that we were carrying real Royal Mail stuff. So Royal Mail were turning up with bags of stuff, chucking it in the back of the aircraft. And we were flying for 4 weeks, scheduled daily flights every single day to prove the robustness and reliability of the mission. It was a real eye-opener for us. We were surprised at some of the conditions off the coast over the Atlantic, essentially. This is where we encountered severe down gusts and 40-knot winds, etc., etc. But we managed to do that successfully. And then earlier this year, we did the Orkney and Shetlands. So we haven't done the top half of this network, but we've done the lower half of this network. Again, flying a network between various airfields, carrying real payload, real Royal Mail parcels and packages around up to Fair Isle. It just so happens my sister happens to live on Fair Isle, and so she was delighted to see this drone come in, this tiny aircraft, and the beginnings of good commercial logistics connections, because these people have to wait ages for parcels. They're just not well connected. She wanted me to put a chicken tikka vindaloo into the payload so she could have a takeaway, but I'm afraid I didn't get around to that. And we got masses of BBC coverage and other coverage. There's lots of stuff on the BBC, lots of videos. If people are interested to click on it and see a bit more. So what lessons did we learn from this? Well, it's perhaps not surprising, but weather, particularly in Scotland, I've spent quite a lot of time in the Shetlands, and it's never not windy. And quite a lot of the time, it's extremely windy. So the aircraft and the system has to cope with wind, of course, and particularly landing in crosswinds. So the aircraft needs to be robust to land in quite severe crosswinds. Our aeroplane would probably always operate if a GA aircraft was like a Piper Warrior or a Cessna 172 is going to fly. So it's quite an achievement. So we're quite happy to fly in quite poor wind conditions and rain, for example. So we were flying in quite rainy conditions. So making sure the aircraft is robust for that and waterproof, and particularly all the avionics is robust is really important. Costs and automation. Well, to be honest, we turn up with a big team of PhD students and engineers. That's not very cost effective, and commercial operations really needs one operator, and in fact one operator flying 10 airplanes concurrently to make the economics worthwhile, and that's something we're well on the road to doing. the aircraft flies automatically, but you need someone, and certainly the CAA insists at the moment that we have a safety pilot to take over at the airfield, to take over if something goes wrong. But certainly the aircraft flies itself. So the person on the ground control system is merely monitoring the health of the aircraft and the status of the flight. What worked well, and in fact, what worked in the video I showed at Lyon Solent was interaction with other airspace users and air traffic control who were initially very suspicious and worried about this, just treated us like another aeroplane. And so in one of the flights back from Faro, there was an Islander aircraft with passengers on, so we were told to hold. That's fine, so we held on the dead side of the airfield. We held for 25 minutes until we had our slot, and we simply, fell in with other air traffic. The Lyon Solent flight was even more severe. It was just at the end of the first lockdown, and a lot of pilots, GA pilots, took the opportunity and were given permission by the CAA to, fire up their Lyconings and Continentals and get the aircraft, because aircraft need to be flown. So Lyon Solent had a really busy circuit, and there were we flying along, having to, mesh with other aircraft. And that worked fine. I mean, there wasn't particularly a problem. But the conclusion from this is commercial operations are now feasible. This technology now means that these poorly connected regions in the world can have something like this, genuinely doing something useful. Now, personally, I don't think the Google and Amazon stuff of drones flying pizzas around cities makes much sense. This does make sense. This is carrying significant payload in poorly connected regions. So that was quite a conclusion. How are we off for time to? Yes, okay, so let me just talk about airspace. So this is work I'm doing in conjunction with Tom Cherrett. We've got two big projects. So there's a thing called Future Transport Zone and eDrone. And this is funding a lot of the, so how do we put in regulations to allow us to fly these things routinely, essentially. And the problem is at the moment that to do our flights, so this was another group who were flying over the Western Isles, we have to use a thing called a temporary danger area, which is a blunt instrument. It's essentially a brick wall. And I fly light aircraft. I fly from Popham and Thruxton. And I would be pretty annoyed if someone put a TDA brick wall across where I want to fly. So these are very unpopular with other airspace users. They segregate airspace, so no one else is allowed in them. So they're very inefficient use of airspace. Etc. And they're temporary. They take a lot of effort to set up. We have to do masses of consultation for a temporary construct. So the exam question is: so how do we change regulations? How do we safely integrate drones with other airspace users? And again, a brilliant undergraduate student who is now a PhD student with us, Alex Pilko, has started that journey by looking at ground risk. And so, for example, what's the best route to take to minimize ground risk? So he's done a lot of very detailed mapping, and open source mapping of the whole of the UK. This one's very interesting because it's actually showing traffic levels, for example, and the change in where people are throughout the day, so that we can actually calculate the risk associated with a given route, for example. And another layer on top of this, it has to take into account wind, ballistic models, kinetic energy. So if your aeroplane is here and it has a problem, and you're likely to cause a great hole in the ground, where is that hole in the ground likely to be? By the way, it's 30 knots wind today. So it's quite a sophisticated model, taking into account all these other factors that are specific to a particular platform type. He's now, so the ground risk work is largely done, but he's now moving on to air prox analysis, so air risk, essentially. Discretizing the airspace, understanding where people currently fly, where the hotspots are, where the pinch points are in terms of traffic, and so that we can route aircraft to minimize air risk and minimize ground risk. So that's essentially what we're doing in these projects. And we've created a concept called Project Lima. And the idea is that if we can find low air risk areas and low ground risk areas, could we negotiate with existing airspace users and set up a thing we'd call the shared airspace zone? And first of all, when we're operating drones here, we publish the flight plans and we give live web-based platform status. The aircraft will have and does have automatic onboard collision avoidance from other aircraft that are transmitting using transponders. So it's heavily transponder based. One of the things we want to play with is a thing called automatic VHF position reports. So an aircraft, a GA aircraft flying nearby can tune to a frequency and the drones will automatically say, I am drone XYZ, I'm at 2,000 feet, I'm on a heading of 300 degrees, and give information so that the pilots don't have to look at any gadgets, they can listen and they can maintain situational awareness, for example. Things called multi-spherical compliance. I probably haven't got time to go into that. So we're working on this in conjunction with other airspace users because we don't want to annoy other airspace users and do things that are unfair to their access to the air. And we're going to do a lot of trials over the next 12, 18 months. We're lucky enough we have a Southampton aircraft that's very well equipped. I mean, it's quite a crude aeroplane in many respects, but it's very well equipped avionics-wide. So it's got lots of transponder technology on board. And what we want to do, and we're doing this in conjunction with the CAA, we have a thing called a sandbox agreement with the CAA to allow us to try drones, try transponder equipment, VHF output, the various flavors of transponders. So there's lots of different transponder types, etc., etc. So we're doing this over the next few weeks to see if we can find a solution to this shared airspace problem. So that's me done. I'd welcome questions or queries or clarification. I'd just like to finish with the final sport for always expect the unexpected. This was us flying Wiltshire, our smallish drone, so 4-meter wingspan drone, and unfortunately we had a collision with a rather beautiful Raptor here, and that could have taken out one of our engines. So it's important to think about redundancy, reliability in this stuff. Okay.
Fantastic. Thank you very much, Jim. Do we have